yesterday it wasn't.
Hi, Joyce!
Now she can hear you. Yesterday there was no.
Yeah, you're gonna hear that every single day, Joyce. Or not. Just FYI.
Alright, here we go. You guys ready? We need to convert, and yesterday we converted rectangular to polar. Last night in homework you had some rectangular to polar. How many different answers can you have when you go from rectangular to polar?
Infinitely many.
Infinitely many, unless they're strict.
Yeah.
And they say 0 to 2 pi or something of the sort. But even then, you could still have quite a few, right? Because you can get to points positively. Explain. How can you get to points positively?
Oh, you start at the right and then go counterclockwise.
Okay, positive angles
and negative. If you go negative to the left, then you go to the same angle.
positively. Let's stick to positive.
Oh, okay.
No negative anywhere in the explanation. So we're going to move from the right and go positive angle. However, what does it take for a radius to be positive? Has to be going in the direction. Has to be going in the direction of the actual angle for the point, right? Mm-hmm. And negatively, it's going to be going opposite. All right. Did we get down the example from yesterday? Okay.
No, I don't think so.
Okay. Let's take a couple seconds. I think this was the whole I'm going to do it fast. And then technically, since we're in calculus, even though it's good to think through in degrees, what should I technically do with the degrees?
Radians.
Yeah.
Is it okay if it's 3 root 2, comma 3 pi over 4 and 3 root 2, comma 7 pi over 4? Or is that wrong?
Isn't that exactly what I just wrote?
No.
You said 3 root 2, 3 pi over 4. Check.
Yeah. 3 root 2, positive, 7 pi over 4.
No. Because think, if you go 7 pi over 4, you're down here, and positive, you're headed that direction, you're over here. So you have to, does that make sense? You have to head the backwards direction from 7 pi.
Okay. So you make the radius negative, and then
for an angle that's opposite.
the opposite.
The actual.
Okay. Yeah.
But I mean, we could do more points. Guys, what are 2 more points? Hold on. What are 2 more points that would also describe this exact location? Because there are infinitely many. Give me another one.
3 root 2, comma, plus 2 pi would be 4 pi over 2, no.
8 pi over 4 plus 3 pi over 4. So 11 pi over 4?
Yeah.
You could do that. Or you could do negative 5 pi over 4, right?
Could you?
Because you could go negative 5 pi over 4.
3 square root 3 over 2. Square root 3 square root 2, and then negative 5 pi over. Yeah.
Because negative 5 pi over 4 will get you back to the right location, and then you could head towards that angle. So there's literally infinitely many that you can do. In homework, did it give you a restriction, or were you just coming up with new ones?
I think you were just coming up with new ones.
You were just coming up with like 2 or 3 or something. Okay.
All
So
right.
what changes? What changes when you're going from? Did I put the wrong title? Hold on. What's up above?
Polar to rectangular.
Oh.
Oh, wait, that is wrong. Oh.
Yeah. Sorry. Can you guys write down literally what I said?
Yes.
Change. I switched my examples for some reason.
Well, while we're on a tangent, Tanner said he'll try and contact you and pick up the item in question.
Tangent one. It's an inside joke from CalcBC. Say hi, Tangent.
Could you do, could it be that you do 3 square root 2, comma 3 pi over 4, and then add 2 pi? To
11 pi over 4.
Could you do that, and then we'll still be right?
11 pi over 4.
That's what you, okay.
Yeah, that's what I did. Or you could do negative 5 pi over 4, subtract 2 pi. Or you could do 7 pi over 4 and subtract 2 pi and then go negative. So many different options. Now, what's different with the polar coordinate? All right, what are you given in the next example? Which means the first coordinate, which is a 4, is really representative of a radius. And the second coordinate, which is pi over 2, is representative of an angle. So I have my r there, I have my theta here. Okay? Now, you could just have memorized, which is a really good idea, and it will be a forever somewhere along the line, but you could have memorized x equals and y equals in terms of polar conversions.
Cosine, x equals r cosine of theta.
And y equals?
Sine of theta.
Technically, once again though, just so we have the concept down, where do these actually come from?
Right triangles.
Right triangle. So if you were to graph 4 pi over 2, technically where is 4 pi over 2? Right here, right? So couldn't you just think about the x and y point? If this is 4 pi over 2, guys, hold on, wait a minute. What's the coordinate if I can see it?
0,4.
Got it. We could just make it as easy as that. So we know what it should be. We know that it should be 0,4. Let's make sure the math actually maps that. Now, it's not always that easy. As soon as you have something off an axis, you can't just count tick marks, sadly. But you can always plug in the radius, cosine of the angle, sine of the angle. And you should come up with the rectangular coordinates, the Cartesian coordinates, for the x and for the y, because cosine of pi over 2 is,
0.
thank you.
Does that mean you're adding up forever?
Wouldn't be a forever, it'd be an endeavor.
Okay, cool.
Endeavor. Maybe if you want another problem, I'll show you the endeavor relationship.
Hey, you never know wrong.
Okay, so then what if, any questions on converting points?
No.
Now, what other parts do we have? Converting equations. And this is where function conversions get a little bit more tricky. Function conversions get a little more tricky. Now, parametric is unique in the sense that it has this third variable t that goes to x and goes to y. However, polar Polar is even more unique, because in polar mode, you literally do not have an x and do not have a y. You can find it. It's possible to be found, but they're not present at all. Parametric, you have x's and y's, you just have this third thing, t. So parametric converting is not all that weird, it's just kind of playing around with a system of equations in some way or another, substitution. Polar, you actually have to use your conversions. But before we talk about conversions, and to be honest, guys, there are really no new formulas to use. We basically have the formulas. And more specifically, we have the key picture trigonometrically to use in the sense of we know that x and y is related to r and theta through a right triangle. And we pulled out some formulas, x equals r cosine theta, y equals r sine theta, etc. But we might have to pull out a little bit more. We might have to pull out a little bit more. Now, as you guys are noticing, question, even though r comes first, and take a second to think about this, even though r comes first and theta comes second, which one is the dependent variable? And which one is the independent? And why is that weird?
Independent is
Theta.
Independent is theta, even though it comes second. Dependent is r, even though it comes first. So that's one thing just to keep track. But the nice thing is, once we start using our calculators, it's like r equals instead of y equals, so it corresponds in that way. Just the way the point is written, it doesn't necessarily strictly correspond.
Isn't it written r theta because otherwise it'd be kind of hard to go an angle and then add a radius?
You could theoretically still do that, but
Theta r instead.
I'm not sure necessarily why the orientation is what it is. It could just be leaving a more complicated number to the end, but I'm not sure the origin of why it was put that way. Of course, I don't really know why horizontal vertical was put that way either. Let's see, where do these problems start? Those are coordinates. Graph a set of points. You can use a table. Ooh, we didn't talk about that, did we? Appropriate window, blah, blah, blah. Do they have you going from rectangular to polar?
Oh yeah.
I don't think they do.
No, they do.
Polar to rectangular.
They'd be going from polar to rectangular.
Oh,
Number 4 is rectangular to polar. Number
But not
1
the
is
equations.
polar to rectangular.
So not the
Those are
equation,
points,
just
though.
the
Equations.
points.
True.
Okay,
Five
so let's get rid of this.
is
We really don't need to stress, I don't think, like AP wise, I can't think of an example when that's necessary. So let's just go ahead and steal this one. We'll go back. I just had a couple pages of examples. This one started in your homework past the point conversions.
maybe go to the dot dot dot.
No, it doesn't work. I'll do control P. Alright, let's start with. Oh, I didn't circle it in this book. I don't know which ones are your homework problems for me not to do.
Hey,
Hey,
you are for us.
that's not how this works.
But it should work like that.
You guys would be weak.
I don't
PC
mind.
students. Okay, what if we were to do something like r equals 2 minus 2 cosine theta? Okay. Now think, we have a right triangle. Don't limit yourself. We actually are going to make endeavors of different things, but don't limit yourself to these formulas in the sense of r squared equals x squared plus y squared, x equals r cosine theta, y equals r sine theta, theta equals tangent inverse of y over x. Just think right triangle. I need to get out of r's and thetas and into x's and y's. But how?
You can multiply both sides by r.
We could multiply both sides by r. It's going to make things a bit more complicated than we necessarily want them to be.
What were we trying to do? Just get.
If we're just trying to convert the equation to rectangular.
Well, f theta will equal to.
Two minus 2 cosine theta is f of theta. The whole thing, right? It's r equals f of theta. I'm just trying to get to rectangular.
You could
You pull out the 2. Yeah.
Can. It's not going to make a big difference.
you could do the thing I said.
Multiply both sides by r, but why?
That way you can get 2x. 2r minus 2x.
True, but then what?
You could move the 2r to the left side and factor out an r.
Okay, so that's one, right? So if we were to multiply both sides by r, we'd have r squared is equal to 2r minus 2r cosine theta. And Gerardo is saying, hey, that sounds fun because then I can just say r cosine theta is x. But now we have to do? I don't know. How do we get rid of r?
X squared.
Isn't r just a hypotenuse? How could we express a hypotenuse in terms of x's and
X
y's?
squared plus y squared.
Square root it, right?
Plus square.
Wait, couldn't we have just done that in the beginning?
I don't know.
Oh, come on.
So, but hold on, what's still the problem?
You have theta.
We have cosine theta. Ah, stink. There's no way to express cosine theta. So isn't there? How could you express cosine theta? Look at your triangle. Who is cosine theta?
Oh,
X
so
over
X over.
Oh. And technically, Gerardo is going to end up the exact same place you were exactly what you're saying there. But what could we replace r with?
How does that simplify matters?
I didn't say it's simplified. I just said that you could have substituted for r in the beginning.
Yeah, that.
So now what?
No.
Where's that rectangle? Stick it to the man.
Stick it to the man. You could stick it to the man.
Yeah.
But who is it?
No.
Oh, we can
What is it?
multiply. It's a circle, right?
No.
But we can multiply.
Mm-hmm. We can get common denominators. We can even move everything to one side if we want.
Yeah, you can get 2 root x squared plus y squared minus 2x, but I don't see where that gets you.
Just technically where Gerardo's would have left us, because this was r squared and this was 2r and that was minus 2x. But you're just solving for what's outright instead of making the creative step and multiplying both sides by r. Any ideas?
Can we just leave it like that?
I wouldn't want to. That kind of.
When
You
you
could.
plug in, everything will just collide.
What you would have to do is probably just move the 2x over. Then you would square both sides, get rid of the square root, and then you would have like a, fourth degree polynomial over here. And then you could move it all to one side and you could solve for y's possibly. But for right now, we'll just stop. That's totally fine. Question, how would you, that's just converting, if you needed to get out of polar into rectangular, into a function with y's and x's all together. How could you, though,
Let me see, that's not right. It has to be all over square root. Oh, never mind.
is that okay?
Yeah.
This is a rectangular one, right? How could you define it, instead of from polar to rectangular, how could you define it from polar to parametric?
What?
Okay.
What?
What? You mean like that?
What?
I don't remember what parametric is.
I don't like this.
Parametric, x is separate than y.
Oh, it's split up.
What?
I don't know.
Well, you'd have to realize that x squared plus y squared equals r squared, and plug that in, and then you can get 2r minus 2x. And you could realize that you could be, well, 2r, r could be a number of things. Oh, sorry, and then you have 2x, so like x would be r cosine theta. Ah, it's simpler than you think, actually. No, I'm not. That's not. I'm doing it all wrong. I'm converting it back to polar. That's-
Oh, she's the formula.
Is that how is it parametric?
Because you have x and y.
X is defined in one variable, y is defined in one variable.
Theta would be in t.
Oh, come on.
That's a good one.
Because x is equal to r cosine theta, remember? Cosine is x over r, move the r over. Who is r? R is 2 minus 2 cosine theta. So just plug it in, plug it in.
Oh, yeah, we're gonna have to actually do
Yes.
Okay.
Let's just say this from polar to parametric is what allows us to take derivatives and find slopes of tangents to parametric curves. Sorry. Slopes of derivatives to polar curves. I said that incorrect. So you might be converting polar to rectangular or polar to parametric. Which one makes a little bit more sense? I don't know. Polar to rectangular, if it makes a nice equation, we can see if it's a circle or a hyperbola or a line. But if it makes a nasty equation, we're like,
So-
right? So then polar to parametric would be wiser in order to be able to get it in or with x's and y's, but without having to get it solely in terms of x's and y's. Does that kind of make sense?
Mm-hmm.
Because ideally, probably, the parametric equations are easier to deal with than the polar. So let's go ahead and do one more thing. What if we were to, I'm not going to have it converting, let's do graphing, because that's in your homework a little bit.
See, those are sweet.
You're just polar graphing.
I'm really good at putting.
There was a picture online. It said polar graphing and a polar bear. Then it had rectangular graphing. And there's like this brown bear, but that was like photoshopped into squares. So, it was pretty funny, actually.
How do we graph? Either you figure out how to use the table really well, or you have to memorize every possible polar graph out there. Struggle. Now, is there a place possibly for memorizing polar graphs? I suppose. But to be honest, it is a small, relatively small topic compared to differentiation, integration, harder integration, and sequences and series. Still in there. Still could be an FRQ. Was it an FRQ last year? Do you remember? Polar areas?
It's like
I know. I'll have to look it up. I'm sure it was on there somewhere. I just don't remember. I think it was on the FRQs though. So it is still important, but to graph is only one tiny step. To graph is only one tiny step. So you could memorize and take like all this mental power to do that and to kill all these brain cells, or maybe strengthen the brain cells. Or you can think about a table. And for a table, whenever you have, let's use our same r that we've been using all along. R is equal to 2 minus 2 cosine theta. Let's think about how we would graph. What are we plugging in?
Theta.
Thetas. What are we getting out? R's. Well, if we're plugging in thetas, and if specifically like this one, if this one has a trig function, well, we want to plug in very strategic thetas, yeah? Meaning unit circle thetas. Ah, trig, it's still important. Yep, it is.
0.
Yeah,
Pi over
that's a great place to start. 0, now, be strategic. You don't want to kill yourselves and have to keep on going to your calculator for decimals if you don't have to. So 0 is great, because cosine of 0 is 1. That's going to be a nice number. Okay, how about pi over 6? Cosine of pi over 6 is root 3 over 2.
Yeah.
Do I have to? I mean, you could.
Pi over 3.
Let's try pi over 3. We could try pi over 3. Now, sometimes you do want to get those decimally ones to figure out what's going on, but let's see if we can just do nice ones. Like cosine of pi over 3 is
1/2.
1/2. Well, that's nice. That's a nice number. How about pi over 2? Yeah, that's not too bad. How about 2 pi over 3? What am I skipping? The pi over 4s and the pi over 6s, yeah?
Yeah.
So, George, what we were talking about is to graph. We can either memorize all sorts of figures, but to be honest, graphing on the AP is not a huge topic. So if we could do a table and not have to worry about memorizing lots of extra stuff, we will. And the reason why, if you notice, George, I'm skipping pi over 4 and pi over 6, yeah? But why? Cosine of pi over 6 is root 3 over 2. That's not going to be a nice, like, I can logically get that number real quick. Okay? So we're trying, like, cosine of pi over 3 is 1/2. That's easier. I'm going to keep on going as far as I can, which would be 4 pi over 3.
What would we have to memorize if we didn't plug in?
I'll show you. Hold on. And then 5 pi over 3.
I had 0,
And
1,
2
2,
pi.
3. Oh. That was fun. Do we have to go that far?
Not necessarily, but it's one of those we're getting used to it. So I'm doing one full revolution and seeing what happens. Sometimes you need more than one full revolution, but if you can figure out the behavior of the graph, then maybe you don't have to worry about doing the entire thing. Now, remember with graphing polar, we talked about how you don't need the polar grid, right? We just need to be able to think polarly.
This is symmetric. This is a symmetric graph, right? Because cosine.
In some senses, but cosine is a different symmetry than sine, so we have to kind of figure that out as well. So if we plug in 0, cosine of 0 is 1, which is just going to be 0, 2 minus 2, right? Cosine of pi over 3 is 1/2. 2 minus 2 times 1/2 is 1, yeah? Cosine of 0 is 0, that's going to be 2. Cosine of 2 pi over 3 is negative 1/2. Ooh, 2 minus negative 1 plus 1 would be 3. Cosine of pi is, where was I?
Negative 1.
Negative 1, good. So 2 minus negative 2 would be 2 plus 2, that's 4. Oh my goodness, it's increasing. 4 pi over 3. Cosine is negative 1/2. Oh, isn't that back to 3? Cosine of 3 pi over 2 is 0. 2 minus 0 is 2. And then cosine of 5 pi over 3 is
2 minus
1. And then what do you think I would
2 pi.
get if I kept on going? Huh. Interesting. Well, let's see what that looks like when we graph it then. Let's see what that looks like when we graph it. So I need to go out 1 and a 2 and a 3 and a 4, right? 1 and a 2 and a 3 and a 4. 1 and a 2 and a 3 and a 4. The more evenly you space it, the more it makes sense, hopefully. And then 1 and a 2 and 3. You guys graph, hopefully not looking at me. See if you can graph it and get a good picture.
You graph it the same way you graph polar, right?
Yeah. So I'm making my pi over 3s right away.
don't have to know that, right?
That's my point. On the right is what you should get. On the left is what you could have memorized to also get. But to memorize the form, limasols will always come from R, oh sorry, not Y. R equals, let's see, we're in polar, not function. But George, this is what I mean. You could memorize this and know every time you are going to get a limasol with a plus. But then you also have to memorize, stink, cosine has symmetry where the first and second quadrant is equal to the third and fourth quadrant. So what is on top of a polar curve will also be on bottom for a function dependent on cosine alone. And then you'd have to think about how it's a negative, so it's going to be facing the left instead of facing the right. There's just, I don't know, a table seems so much easier to me. Now, somewhat getting used to polar is kind of understanding that you are going to be rotating around. Once again, I said it's not impossible to get a line in polar. But almost always, if you can think about it, between 0 and pi over 3, the cosine values are between 0 and 1/2, always increasing. So it starts small and it gets bigger and bigger, and it's going to keep on going. As it gets more negative, then it's going to start decreasing until back to 0. So based on the nature of cosine, I can say I can connect it in that curve. Does that kind of make sense?
Yeah.
Is that the only kind of limason that we can get?
No.
No. I'll give you
You
another one.
want to twist.
What if I was to give you?
Yeah, there's one of those.
Misty, when we convert from polar to rectangular, are we most of the time going to get like a conic section?
If they're asking you to convert, yeah, probably. Otherwise, if it's a limason, you probably won't be converted. What about to give you something like r is equal to 1 plus 3 cosine. Let's do a sine,
No.
just to change that. That would be fine. Okay, you guys sit up your table and go. And so far, have we done any calculus whatsoever?
Yes.
There was some calculus in the
Not
homework last night.
Trig.
Not
Trig is
prepared
in
actually.
calculus. Does that count?
I'll give you a couple at the end just to see what you could do. So I give you, 39.
Yeah.
Does trig not
Thank you.
count as calc?
72 I got true.
It counts as pre-calc. It counts as foundation calc. It counts as elementary math.
Elementary math? Since when? I just learned it like, what, 3 years ago? And where's the bleach?
Bleach.
What elementary school were doing when I took me like my life to learn? It's not cool, dude.
You guys got papers.
How many calc AB students do you have?
I think it's not past 60, somewhere between 50 and 60. There's a lot of them this year.
Dang it.
There's so many for you guys to peer tutor. Oh my god.
No, because I was gonna say,
It's
if we had like
37.
20 kids, or like, if we had less calc kids, then all of us during the AP exam could cheat together. Because there's less of us now, like, there's less of a chance that
George, focus on.
just thinking. You could like pull out our calculators on the non-calculator part. You'd be like, yo.
No, anytime I have a small BC, ABs are usually pretty big. Anytime I have
And
a
it's
big
gonna have a
BC,
big
ABs
piece.
are pretty small. Alright, my turn. You guys keep going.
Wait, should I?
Why am I doing horizontal side tables when I could be doing vertical?
Space.
Because the AP does it this way.
Should I do pi over 6s instead of pi over 3s?
I would,
I
right?
would.
Because then sine is 1/2. Just being strategic. I put my arm data in the wrong place.
nasty, George.
They're very nasty to be a teacher right now.
They're worse than the last ones.
I agree.
Love got busted now. Okay.
Oh shoot, messed up. Miss D, 1 minus 3 is negative 2, right?
1 minus 3 is negative 2.
Yeah, I can't do addition. Did you guys figure out what it looks like?
I think it's a Lima song with an inside loop. I'm not finished cracking yet.
It's actually not bad. Okay.
Hmm?
The graphing is fun.
I think it's interesting. So technically D.
There was not a point at 0, 0, right?
You can memorize. There's always going to be a Lima song with an inner loop whenever A is less than B. Why? Because sine and cosine can be positive 1 all the way up to that or negative 1 all the way down to that. And if A is any number that is less than the coefficient, and you have negative 1, you're going to have a negative radius, which is going to turn in on itself, hence the inner loop, and then cycle around. Right here. And it went back a half. Because it's negative. Say if you have 11 pi over 6, it went back a half. Now in both of these, it took 2 pi to complete a cycle, right? What would change so that you wouldn't need 2 pi to complete a revolution or a cycle of the graph?
Double line.
Yeah, maybe like it'd be sine of a double angle or sine of a half angle. That's going to change the period, right?
If it was sine of 2 theta, it would be from 0 to pi would make it a whole. Okay.
So let's check out one more graph, and then I think we're almost done. If you guys check out in your homework, first of all, really quickly, I gave you number 39 just because I was like, I wonder what they do. It's not because I actually said to be able to take a derivative without us talking about how to take a derivative of a polar function. It's just interesting to think about. But that's definitely coming second semester. So number 39, don't stress about. And what did I give you?
72.
72
And 60.
and 61. 61 should be really easy to answer, hopefully.
Yeah, 72 was.
72 is interesting. I don't know. I thought was, out of all the later ones, that one I was kind of like, that's kind of cool. But here's the idea. Homework really up to number 29. Homework really up to number 29 is what I'm kind of more not worried about, but where I would focus. Why am I saying where I would focus?
Because that's what they're going to ask us in the AP.
Because what do you have tomorrow?
Test.
Oh, we need first.
No, not a test. Not a test. I'm not going to have a test on these 2 sections. It's pre-calc, but it's just pre-calc. Some of you have never seen it, some of you haven't seen it in a while, and some of you still we need a refresher on. So we're just going to have a quiz. It's going to be small. We're going to go over homework questions first thing tomorrow, okay, on homework number 2, section 11.3. Part 1 is only because there's a whole other part of this section that we'll get to at the end of the year. Unless I decide to do it before sequences in series, but I don't think so. I think I'll probably leave it in the order that they have it, which isn't a bad thing. So tomorrow it's just basically, can you operate your graphing calculator? Can you eliminate the parameter for a parametric? Can you figure out a proper window or a proper T-range to see the whole graph? Polar. Can you convert points? Rectangular to polar, polar to rectangular. Can you do homework problems up before number 39 or wherever that one is? 39 you don't have to worry about. 39 on is just kind of like extra for free, kind of fun. If we have time after the quiz, we'll look at it. Does that sound good?
So, and everything up to
36.
20? Everything up to 30, including 36?
Oh, Gerardo, when you text us at like 4 o'clock, we're probably also in practice.
Oh.
So like,
We're not ignoring you.
yeah, just.
I was probably with kids.
Like I didn't start my homework until like.
It's okay. That's probably going to be me next semester.
I mean, I think
Like R prime?
you're out by like.
Because that would be
Yeah,
DRD
I'm
theta.
out
That
by
wouldn't have anything to do with the graph
7.
and dy and dx.
So yeah, that's why we.
So it would be a rate, but it wouldn't be a tangent. Does that make sense?
Misty, are you gonna be here after school? Oh, do you know how late?